Hey everyone, Nitesh this side. Hope you're doing good. So let's start with the question. So the question is trim a binary search tree. Okay. So what you have given a root of the binary search tree and the lowest and highest boundary as low and high. Okay. So what you have to do, you have to trim the tree so that all its element lies in this range, low to high. Trimming the tree should not change the relative structure of the element that will remain in the tree. That is, any node descendant should remain a descendant. Okay, it can be proven that there is a unique answer. Okay, so what you have to do, you have to return the root of the trim binary search tree, not that the root may change depending on the given bounds. Okay, so let's understand with an example. Let's take this example. So we have given this example 0 or basically 1 0 2, and this is our root node, and we have given a range of 1 to 2. Okay, so we have this 0 or sorry 1, then 0 and 2. Okay, so what you have to do, you have to just maintain the root node only which are lies in this range. So your range is 1 to 2. Okay, so this is 1, you can remain as it is. This is 2, this is remain as it is, but this 0 is not lies in this range, so you will remove that. So this is the final output for this. Okay, let's take this example. So we have this 3 0 4 2 1. Okay, your range is 1 2 3. So this element lies in this range, so you will not do anything. Now this element is not in the range. Okay, so you have to remove it. Okay, you have to remove it, but after removing it, you have to give some another node in this, like you have to go deeper if there is node existing. Okay, so as you can see, this 2 lies in this range. So what we will do, we will just basically 3 left is now this 2. Okay, and after this you will go in this direction, so this is also lies in this range, so you will keep remaining the same range. After this element is not in this range, so you will take this out, so your element become 3 2 1. Okay, so I hope question is clear to you. So let's understand how we can approach this question. Okay, before going through the approach, so let's understand what is BST. So BST is the binary search tree. So what that mean is, so let's say this is your root node. Okay, and let's say this is your left subtree. Okay, this is left subtree, and this is right subtree. So on the left, like on the left subtree, all the values in the left subtree is lesser than the root value, basically root dot value, and all the value that are greater, like on the right side, are always greater than the root dot value. So it is always greater than root dot value. Okay, so let's see with an example. So this is your root node, this is your you can say node, then this is 2, and this is 3, and this is 7, this is 6, this is 5. Okay, so at every node, your left element is always lesser and your right element is always greater. So as you can see, this is your root node. All the element in this left subtree are lesser than this, and all the element are in the right subtree are greater than this. Okay, so if you see for this example also, so for this node also, like in the left it's having null, but on the right all the elements are greater than that. Similarly, if you can see for sorry, this will be 8. Okay, by mistake it's done. So if you see for this node, yeah, left node is always lesser than and right node is always greater than. Okay, so now BST is clear to you. Now let's see how we can use this property to solve this question. So let's understand with this example. So we will use the same property of BST that we just understand, that the left value is always lesser than root dot value and right value is always greater than root dot value. Okay, so what we will do, we will check whether the current node, if it is lies in this range, we will search its left element, we will go to its left element and we will go to its right element. Okay, but if it is not in this range, we have to do something. Okay, so it will be like, if your root dot value is greater equal to low, and root dot value is lesser than high, basically it's in the range. So what we will do, we will call the left element. Okay, so solve basically left root dot left, and similarly we will call the right part. Okay, solve root dot right. Okay, so this is the one condition which we will handle. Okay, so what we will do, we will check for this element. So as you can see, this 3 lies in this range. We will call its set its left element, we will set its right element. Okay, now call comes to here. Okay, so for 0, this element is not in this range. Okay, now what we can use is, we will use the binary search tree property. How we will use at this point is, let's say this is also having a negative element. Let's say this is -1 and this is also -2. Okay, now if it is like it is having the left subtree also and it is having the right subtree, how can you identify whether you have to set this -1 at this position or 2 at this position? So what we will do, we will not go to its left and we will not go to its right. We will go in only in one direction. How we will go in only one direction is, we will check whether the element, so what we will check, basically if our root dot value is lesser than our low. So low is this basically, and this is your high. Okay, so if it is lesser than, what we will do, basically in a binary search tree we know left part is always lesser than. So if our root value is lesser, then its left part is also lesser, so it doesn't make sense to go to the left part. Okay, so what we will do, we will not go here and we will search only in the right part, because there is a chance of getting a greater element than our root dot value. Because if we go in this direction, we can't find a smaller element in this range, sorry, greater element. So we will not go in the left part, we will go in the right part. Okay, so what we will do, we will change our now root is equal to, so we will call the right part, and same for vice versa. Okay, so else if your basically it will be like root dot value is greater than high. Okay, so there might be a situation like the current node is greater than your range, so then also it doesn't make sense to go in the right subtree. If it is like, let's say this is 4 and this is 5, but your range is only 3. Okay, so we will so if we go in the right direction, we have the greater element and we don't want this element also, because we have to remove this. Instead of this, we have to take either 3 or 5. Okay, but the chances of getting the smaller element for the right case will be in the left side. Okay, so same for right part, is going in this direction doesn't make sense because it will always have the greater element. Okay, and we need the smaller element, so smaller element we can only find in the left part. Okay, so what we will do, we will just go in the left part, and after that we just return our root. Okay, so let's solve our problem. So we are at here, we call this 2. Okay, after this we check that the element is in this range. Okay, so what we will do, basically we will call its left and we will call its right. Okay, now right is basically left is also in this range. Okay, so similarly it will call its left and it will call its right, but they both are null, so this is our base condition. If root are null, so we just return from here. Similarly we so after this one will be returned to the root dot left. So this is, let's draw it like this. So we have set this one. Okay, now this 2 is set at here. Okay, now after this what we will do, the right part also return its element, so this will return null only. Okay, so this is like having a null at this position. Now after this this is not the right part. Okay, so this is just returning the root, because here you can see this is we are returning root dot left, root dot right, but here we change our root because that element is not in this range. Okay, so we just directly return this. It's just like uh, one sec. So here we change our node, and this node is now become this point to this. Okay, so this left is now pointing to 3, and now the call goes to the right part. Okay, so now as you can see the element is greater than this range, so what we will do, we will call its left part. Okay, now left is null, so it just return null, and but this will not return here, this will return here because we have changed our root whenever our element is not in this range. So as you can see we have changed our root. Okay, so this will having a null here. So this will be the perfect output by giving this in this range. Okay, let's write the code for this. Okay, so what we need is we will first check whether the element is in the range. Okay, root dot value is less than high, will do something. Else if your root dot value is lesser than low. Okay, in this case we do, else we do something. Okay, so this means that root is in the range. Okay, so what we will do, we will call its left part. So left 𝗵𝗃 root dot left, we will give low, we will give high, and similarly we will call its right also. 𝗵𝗃 root dot right, low, and a high. Okay, now this else if condition is talking about if root dot value is less than low. So after this it doesn't make sense to search in left part, so we will search only in right part. Okay, like if this question is not BST, then you have to go in all the direction, but this is a BST, so you can basically skip that. So what we will do, we will change our root, and basically we call 𝗵𝗃, we'll call the right part, and we'll give low and high. Okay, and this else is the opposite of that, so root equal to 𝗵𝗃 root dot left, and we'll give low, we'll give high, and after that we just return our root. Okay, I think we have covered all our recursion case. Okay, the base condition is left, so base condition, which is if your root is null, you just return the null from here. Yeah, let's cover all the logic, so let's run it. Hope it will run at single try. Yeah, this is accepted. Let's submit it. Okay, the time complexity for this is like if element is always in this range, so you will go to all the elements. So at worst, you can say at worst case you will go iterate all the elements, so that is order of n elements basically, whatever the root children are there, so it will be order of n for that. And space is, you can say we are using a recursion space, so if you want to calculate that, that is also order of n, otherwise it's a constant space complexity. Yeah, hope you like it. Thank you for watching my video, and do join that Telegram group if you have any doubt and any concern. Thank you.